Nature has a way of letting us know that we are not the most powerful force on Earth. Hi, I'm LeVar Burton, and I'm going to take you on a journey which will expose a defiant and dangerous enemy that already lives and thrives among us. I'm not speaking about some new Hollywood blockbuster, but a real and present danger within the world we live. This natural occurrence is eating away at our structures and equipment. Some of our nation's most important systems are feeling the full brunt of the enemy's effect, including our transportation, public safety, and military systems. So, what could this enemy possibly be? It's corrosion, a silent, pervasive, and unrelenting scourge that destroys the very items we count on every day. The war being waged against this invasive enemy should not be taken lightly, as it costs our government, industry, and individual citizens billions of dollars a year. Now, you and I certainly know rust when we see it. Just look around and you may see rusty bolts or even spotted or pitted surfaces on old vehicles as they drive down the road. Now, that's the corrosion that we can see, but it's what we can't see that's even more troubling. The fact of the matter is that corrosion occurs naturally. If materials aren't treated to resist the effects of corrosion, they will deteriorate. It's really just a simple law of physical science. After we change the physical characteristics of a metal, it simply wants to return to its natural state. We may heat them, draw them out, pound on them, mix them with other materials, and manipulate metals to make them stronger or more flexible, or sometimes even both. But unless we prevent it, these materials will eventually corrode. It is this deterioration that results in the failure of many important systems. Rust is the reason I'm here to speak with you today. It's an unfortunate fact that most of the billions of dollars spent each year on corrosion are focused on inspection, treatment, and repair. But what about combating corrosion before it occurs? The general public does not give corrosion much thought until something happens which brings the topic to the forefront of the media and our minds. It's only when corrosion directly affects our lives that we worry about it. Will our brakes fail due to corrosion? Is the bridge that we're driving across safe? Or is that important bolt holding that crane high above our heads corroded and about to break? Fortunately, there are many companies and government organizations currently implementing strategies for combating corrosion, which will save lives, prolong the life of products, protect our valuable assets, and ultimately cut costs. The fact is that corrosion remains a mystery to many of the important people you and I rely upon to keep our infrastructure operating. Designers and engineers don't always select materials that resist corrosion. In some instances, they even unintentionally create designs and manufacturing methods that actually promote corrosion. All too frequently, decisions are made to avoid the initial cost of corrosion prevention, and this results in even more money being spent in maintenance over the lifetime of a product. So the problem is left to the customers who unknowingly buy corrosion-prone products, and to the decision makers who may hire technicians to find and repair the results of that corrosion. Technicians are not always adequately trained in critical processes to recognize, evaluate, treat, or repair corroded materials. As everyday consumers, each of us has to bear the responsibility for accepting products, equipment, systems, and structures that are going to corrode. What would be the end result if we didn't spend billions of dollars each year to combat corrosion? One result would probably be a crumbling infrastructure. Bridges, buildings, roads and runways, all would eventually deteriorate and become hazardous and finally useless. In addition, our nation's entire transportation system would eventually disintegrate and become unusable as well. Manufacturing and control machinery in plants, mines, and utilities would rapidly become unserviceable. Many of our military's weapon systems would cease to function effectively, causing the country to be virtually defenseless. But the billions of dollars we spend each year represents only the annual direct cost of treating and repairing corrosion. Studies suggest that the indirect costs of poor design and unrepaired damage could be several times this yearly direct cost. So, what is the answer? Well, Executive branch and Government Accountability Office studies suggest that by investing in the prevention of corrosion, rather than waiting to treat, repair, or replace corroded materials, would reduce the annual price tag by as much as 40%. For many years, professional corrosion societies, educators, the military, and Congress have recognized the widespread effects of corrosion. In 2002, Congress directed the Department of Defense to develop a program to improve corrosion prevention and control. The department defined several paths to transcend the ways in which corrosion has been approached. In addition, other executive agencies joined the department to address common corrosion concerns. And this new approach has also helped to expand academic interest. Corrosion education is one of the greatest weapons we have in our arsenal in the fight against corrosion. And Dr. John Scully fights this good fight every day.
Well, universities fulfill 3 or 4 crucial roles that help the country with corrosion control. And I'll mention briefly what those are, but the first and foremost is education, so that we have corrosion-savvy engineers and scientists in all facets of society. And second is research and development, and there are a lot of grand challenges in the corrosion area, particularly today, because today we have an aging infrastructure, we have some things in the highway and also in other aspects of industry and government that are getting quite old. And the last area, last but not least, is technology transfer. And that is to move things from the university, from a benchtop level to the field level, or to an actual marketable device or corrosion control strategy.
There's no mystery that corrosion behaves according to the laws of thermodynamics. The mystery is how these laws apply to specific corrosion scenarios and why these scenarios occur. Bill Abbott's lifelong work has been to define and monitor the effects of the atmosphere on corrosion.
Over perhaps the last decade, there's been a major effort underway within the military to understand the real field environments in which we're deploying or storing equipment. Work has been done around the world to try and provide hard data on these effects, and at the present time there really is a very good understanding of where we're using such assets. What we're finding is, in terms of atmospheric effects on equipment, there's probably about at least a 100-to-1 difference in the severity levels of real environments. Now, this work is being done for more than just academic purposes, because even today, hard decisions, for example, where we might base or rebase assets, are really being made. One of the things that's being realized is how we test things back in the laboratory, or try to simulate what we're seeing in the real world. This has always been a real problem, and it's been known that we have problems in this area. Well, it's turning out that virtually all of the tests that we use at the present time have difficulties associated with them, and in fact, very few, if any, really simulate what we're seeing in the real world.
So, how does corrosion occur? Well, the source of all corrosion is an electrochemical cell. To understand the mechanism which is capable of producing so much good or causing so much damage, let's take a closer look at the electrochemical cell. Now, to do this, I'm going to request that our corrosion assessing simulation system join us in our presentation. Cass, please show us the file for the electrochemical cell mechanism.
Of course, Mr. Burton, but may I first say that your reputation precedes you, and it's a pleasure to be working with you on such an important project. All electrochemical cells consist of 4 components. First, there must be an anode, where electrons are generated through an oxidation reaction, such as metal corrosion. Second, there must be a cathode, where the electrons, liberated from the anode, are consumed by a cathodic reaction. Third, there must be a metallic conductive path that physically connects the anode and cathode. The anode and cathode might be 2 different metals that are electrically connected, or they might be different sites on the same piece of metal. Finally, the metal must be exposed to an electrolyte consisting of solution that contains and transports ions and contains a cathodic reactant. These four components must be present for corrosion to occur, or for the operation of any electrochemical cell, like a battery. Electrons, liberated during oxidation, move freely along the metallic path, but do not move freely in the electrolyte. Conversely, ions move freely in the electrolyte, but not along the metallic path. It should be noted that an ion is an atom or molecule that has lost or gained one or more electrons, making it positively or negatively charged. A negatively charged ion, which has more electrons than protons, is known as an anion. A positively charged ion, which has fewer electrons than protons, is known as a cation. In corrosion, the corrosive environment is the electrolyte. A typical corrosive environment is seawater, which contains chloride and many other types of ion. Other corrosive environments might be a liquid, held in place by a solid substance, such as soil or concrete. Metal corrosion is the destructive dissolution of metal through an oxidation reaction at the anode of an electrochemical cell. Metal atoms oxidize to produce positively charged metal cations, such as zinc 2+ or iron 2+, that are released into the environment. The electrons released by the oxidation reaction travel through the metal to the cathode. As with all electrochemical cells, corrosion requires a cathode where the electrons, liberated by the corrosion reaction at the anode, are consumed by some reduction or cathodic reaction. The rate of metal corrosion or oxidation at the anode is always equal to the rate of reduction at the cathode. This reduction reaction consumes cathodic reactants, usually supplied from the electrolyte. Typical cathodic reactants in corrosion are hydrogen ions, dissolved oxygen or water, but can involve other species. In acids, the primary cathodic reaction is the reduction of H+ ions to form hydrogen gas. In neutral environments such as seawater, the concentration of H+ ions is low, and the cathodic reaction is often the reduction of dissolved oxygen gas molecules to form OH- ions. Cations migrate and diffuse through the electrolyte to the cathode, while anions migrate and diffuse toward the anode. Electrochemical cells that form on corroding metal surfaces or in metal cracks or crevices require these four components and behave in the same manner as batteries. The difference is that the electrical current produced by a battery is captured to light a bulb, start an engine in a car, or power a device such as a laptop computer. Corrosion cells behave like a shorted battery, where the anodes and cathodes are directly in contact with each other, or even at the same or microscopically separated sites across the same piece of metal. The local anodes and cathodes might move across the surface of the piece of metal, resulting in uniform attack. In this arrangement, the electrons cannot be captured and used for any useful purpose. In a battery, the separation of anode and cathode and the travel of electrons from the anode to cathode through this circuit enable the electrons and electrical energy to be used, such as in the example of the light bulb. So, in our attempts to thwart corrosion, we try to design structures and components to eliminate at least one of the four electrochemical cell components, and thus prevent the oxidation and reduction reactions characteristic of electrochemical cells.
Now that we understand the fundamentals of corrosion, let's go to the Navy's Carter Rock Laboratory located just outside Washington, D.C., and see corrosion in action.
Accessing Carter Rock Laboratories program. Program running. Here we demonstrate the mechanisms associated with the corrosion cell. Remember, the corrosion cell must form a completed circuit through an anode, a cathode, a metallic path through which electrons flow, and an ionic path through which an ionic current flows. So, if you remove the ionic path, which is an electrolyte as shown here, ions cannot flow between electrodes. If you remove either the anode or cathode from the electrolyte, the current passing between the anode and cathode goes to zero. Since current is proportional to the degree of corrosion, zero current means zero corrosion. Since the degree of corrosion is proportional to the current flow, any physical characteristic of the corrosion cell that increases current flow will increase the rate and degree of corrosion. One example is the ratio of anode to cathode surface area. The amount of electrochemical reaction on the surface is proportional to the area exposed to electrolyte. In the beaker on the left, the large piece of aluminum is the anode, and the small piece of steel is the cathode. The aluminum is being oxidized, providing a flow of electrons to protect the steel. Since the steel cathode is small, it demands very little current, and the aluminum anode is easily able to supply that current. In the center beaker, the anode and cathode have the same area. Here, more current is required to protect the larger steel surface. The beaker on the right has a large steel cathode and a small aluminum anode, so the steel is drawing more current from the aluminum to try and protect the entire steel surface. This experiment demonstrates that you should design systems so that the surface area of metals that could be anodes are significantly larger than the surface area of metals that could be cathodes.
Let's take a look at some additional clues regarding characteristics and properties of materials that affect why and how fast they corrode. Run program.
Running. This is what we refer to as the galvanic series in seawater. We rank metals from the most stable to the most reactive by measuring their electrochemical potential when exposed to seawater. The metals at the top of the galvanic scale are referred to as noble metals, and they have the most positive potential. As the potential of a metal becomes more negative, there is a tendency for the resistance to corrosion to decrease. So, on the left, we see that titanium has a potential of about minus 0.27 volts relative to the reference electrode. On the other hand, zinc, which is the least noble metal in this demonstration, shows a potential of less than minus 1 volt. The corrosion rate often, though not always, increases as the corrosion potential decreases. In this case of seawater, titanium has a much higher potential and is significantly more resistant to corrosion than zinc. The other metals exhibit potentials between these extremes. Extremes between chemical substances is demonstrated when a sodium solid is introduced into water. The galvanic series is useful for predicting the interaction of different metals that might be electrically connected and then exposed to a corrosive environment. The combination of materials far apart in the galvanic series can result in accelerated corrosion of the less noble material. This is called galvanic corrosion. In general, the galvanic connection of materials that are close to each other in the galvanic series results in very little acceleration in corrosion compared to the uncoupled condition. In this experiment, the galvanic cell features two dissimilar metals, nickel aluminum bronze and zinc, as electrodes. We will show how the distance between the electrodes affects corrosion. The most intense corrosion occurs at the interface between the two metals. As we move the metals further apart, the electrolyte provides more and more resistance in the ionic path, so we expect less corrosion. We measure the corrosion rate by observing the current between the two materials. Here, you see about a 30 milliamp current. Notice that as the experimenter slowly lifts up the nickel-aluminum bronze electrode, the spacing between the metals increases and the current decreases. In the context of what we have been demonstrating, batteries are controlled galvanic corrosion experiments, or more properly, electrochemical cells where electrons between physically separated anode and cathode are captured. Here, we generate sufficient current to power a light-emitting diode by using the galvanic interaction between different metals. The three corrosion cells use materials that are far apart in galvanic series. The LED lights up when connected to these galvanic cells. Adding additional galvanic cells or using materials that are further apart in the galvanic series would produce more electricity and cause the light to become brighter.
Cass has shown us the basic operation of the corrosion cell and how it wreaks havoc with our metal structures and equipment. And now, we're going to investigate each of the 12 common types of corrosion while looking for evidence of how they occur and for clues as to what we might do about combating the havoc they create. So, let's start our detective work with the most common type of corrosion. General corrosion, also known as uniform corrosion, occurs when a metal or alloy is placed into a corrosive solution. Cass, please run the simulation program General Corrosion.
Simulation program. General corrosion. Running. General corrosion is usually described by the depth of attack over time. It may also be described as a loss in metal thickness, or as a rate of penetration, where the depth of penetration after a period of time can be estimated. This video shows the corrosion of low-carbon steel, which we find in auto bodies, bridges, and handrails. This is termed uniform corrosion because the entire surface appears to be corroding all at once. The video shows this is not exactly true. You can see that corrosion is initiated at many points on the surface and rapidly expands with time to cover the surface with an apparent uniform rust film. Corrosion probably initiates where there are impurities or at points that are slightly chemically different from the surrounding material. Eventually, the attack moves around and becomes more or less uniform. The clock shows how fast this process occurs on unprotected steel. The next example is also of uniform corrosion to show how rapidly a bare magnesium alloy, as used for a helicopter gearbox, may corrode under adverse environmental conditions. During the first few days, weather conditions were quite dry, even in this severe coastal environment. Suddenly, weather conditions changed as it began to rain, and we see a rapid acceleration of corrosion in this important material.
Now, the next type of corrosion we're going to look at is galvanic corrosion. And as its name implies, it is corrosion due to the galvanic action between two or more dissimilar metals, alloys, or electrically conductive nonmetals. This is one of the more common forms of corrosion in complex components because of the wide use of dissimilar metals in the design and manufacture of equipment and structures. Cass, run the galvanic corrosion simulation.
This sequence of pictures shows the characteristic appearance of a mated couple between an aluminum alloy and steel. What is actually happening is that the aluminum alloy is corroding much faster than if it had not been joined to the steel. Also, the steel is corroding slower than if it had not been coupled. In many galvanic couples of this type, the very severe corrosion actually occurs in areas that are difficult to inspect, such as the interface of the metals. What you are now seeing in this sequence of images is what the interfaces look like when the samples are opened and the effects are viewed. The conclusion that can be reached from this is that what we cannot see may be the corrosion of most importance to actual equipment. This last photo shows a practical example in the field of the effects of improperly coupling dissimilar metals of brass and galvanized steel. Severe corrosion is evident. Program Galvanic Corrosion complete.
Now, we're going to take a look at pitting corrosion, which occurs on the surface of metals, leaving pits and craters that may rapidly penetrate the metal.
Running program. In pitting corrosion, the attack is focused at a small area. The surface surrounding the pit might or might not be corroded. Pit shapes range from broad, shallow pits that are called craters to narrow, deep pits. The illustrations show the characteristic appearance of pitting corrosion. Pits can have many shapes. This example shows the appearance of pitting corrosion on aluminum alloy in a severe coastal environment. The white features are actually mounds of aluminum corrosion products. Pits are formed when a small surface area is attacked at a greater rate than the surrounding surface. Pitting results from localized breakdown of an otherwise protective and very thin corrosion-resistant oxide film that forms spontaneously on many metals. Pit functions as a local anode, and the surrounding surface area acts as a cathode. Once a pit initiates, it tends to grow. This photo shows what has actually happened to the metal below the surface when the corrosion products are cleaned away. Metal has been removed by corrosion and is not readily apparent by inspection. It is this aspect of pitting corrosion that may have a significant effect on structural integrity. Here, we see time-lapse photography of a stainless steel surface. The gray square at the top is a 400 by 400 micrometer surface, anotically polarized so pits, seen as black spots, develop at microscopic inclusion sites. The green and red markers indicate whether pits are formed initially at a particular site or whether they die and are reborn as active pit sites. The middle plot shows the cumulative number of pits formed, while the bottom plot shows the total metal oxidation current versus time. The spikes correspond to individual pit formation and death. The increase in current reflects the cumulative effect of individual currents from all growing pits. End program pitting.
Crevice corrosion is localized corrosion that occurs in or adjacent to mating surfaces between two metals, or between metals and nonmetals such as gaskets. It's similar to pitting corrosion in that it's usually the result of a breakdown of a protective oxide film.
Crevice corrosion program running. Crevices can form under less aggressive conditions than pitting, and so are very dangerous. Crevices are commonly found at many interfaces between two materials that are not perfectly bonded together, such that there may be a very small gap between the two, which we call a crevice. It is within this crevice that water and other chemicals may be tightly held to create a very aggressive chemical environment. The video shows a couple of aluminum mated to graphite. The time sequence shows the pitting corrosion of aluminum, and to visual appearances is not much different than the corrosion we have seen earlier for aluminum in this environment. However, the last photo shows what is really happening to the aluminum when we open this interface for inspection. It shows very severe corrosion and deep pits. All of this happened within 6 months of exposure in the coastal environment.
Most metals used in engineering applications are not pure metals, but a mixture of two or more elements designed to achieve specific properties. These mixtures are known as alloys. For example, steel, our most common alloy, is a mixture of iron, carbon, and other elements. Dealloying, the next corrosion we're going to observe, is the corrosion of one or more of the component metals of an alloy. The remaining materials may retain the original size and shape of the alloy, but has greatly reduced strength and ductility. Cass, let's take a further look at dealloying, shall we?
In this animation, a nanoporous structure is created by selective dealloying of zinc from a brass alloy. This alloy is called a binary solid solution alloy, where copper and zinc atoms are mixed. On an atomic scale, zinc is soluble in copper, and conditions can be created where only zinc can dissolve. Here, zinc is oxidized and released as zinc ions, while the copper atoms remain behind in an unoxidized state. The remaining copper atoms rearrange and form very narrow channels. The copper surface area increases many times over a period of time. While the animation shows rapid dealloying, actual dealloying may take days or months.
Thank you, Cass. Now, let's take a look at intergranular corrosion. Metals and alloys have crystalline structures. This means that atoms have periodic alignments or stacking of many atoms in atomic planes to make a crystal. Most commonly used alloys are composed of aggregates of small crystals called grains, where one periodic stack of atoms forms a crystal interface with other stacks having slightly different orientations. The resulting aggregate is called a polycrystalline material. The regions where these grains meet are called grain boundaries. These regions can have a different composition and structure than the individual grains themselves, and sometimes this difference in chemistry and structure leads to a more corrosion-prone grain boundary. When corrosion occurs preferentially at the grain boundaries, it's called intergranular corrosion.
This is an example of exfoliation, which is intergranular corrosion of an elongated grain structure, resulting in a flaking off of the grain layers. The aluminum alloy shown is particularly susceptible to exfoliation when joined using steel fasteners. If the fasteners were aluminum, intergranular corrosion would have progressed more slowly. As time progresses, you can see the aluminum around the periphery of the fastener beginning to lift and eventually appears to come apart. This photo is a metallographic cross-section of the sample just shown. It is apparent that there is substantial metal loss in all dimensions, which may affect structural integrity. End program.
Stress corrosion cracking is the corrosion-induced propagation of cracks when the material is under tensile stress while being exposed to a corrosive environment. The tensile stress may be due to an applied load, residual stress from forming and fabrication, or a combination of the two. It's particularly insidious because the combined stress and corrosion can cause unexpected structural failure. Cass, please give us some more information on stress corrosion cracking.
Stress corrosion cracks can appear as fine, brittle, irregular cracks along the metal surface and into the metal. The illustrations show the characteristic appearance of stress corrosion cracking. The actual mechanisms that cause stress corrosion cracking are still unclear. Stress corrosion cracking usually involves a specific metal in a specific environment and is often accelerated by increased temperatures. Sometimes, a single environmental element such as chloride ions, ammonia, methanol, seawater, or sulfides present in small amounts will induce stress corrosion cracking. In this video, an aluminum alloy used in aerospace structures was subjected to high tensile stress in a corrosive environment, where both stress and corrosion contributed to material failure. The video shows slow but discernible corrosion over a period of several weeks. However, close examination of the photo sequence indicates that the entire process, from the first slight visible crack to total sample failure, probably occurred over a period of no more than 3 to 4 hours. This occurred in 3 stages: crack initiation, crack propagation, and fast fracture of the remaining cross-section of material. So while stress may be applied for some period of time, once corrosion is initiated, failure may be sudden.
Hydrogen embrittlement can be described as the absorption of hydrogen that promotes brittle fracture of the metal crystalline structure. The results of hydrogen embrittlement are various forms of cracking similar to that encountered in stress corrosion cracking. Cracking can be intergranular or transgranular and is more prevalent in alloys with a high yield strength. Corrosion fatigue is the result of alternating or cyclic stresses of metals in a corrosive environment. A fatigue fracture is usually transgranular across the grain of a metal. Flow-assisted corrosion, or erosion corrosion, occurs or is accelerated when there is relative movement between a metal and its environment, such as the flow of fluids through pipes. Fretting is direct wear that's due to the motion between two surfaces that are under load and move relative to one another. The relative movement is usually cyclic and occurs at a fairly rapid rate. Fretting of either surface accelerates and increases the effects of corrosion. And lastly, we'll take a look at stray current corrosion. This kind of corrosion can occur in almost any metal that's been buried in the soil or immersed in water. Sources of electricity throughout equipment and facilities may provide stray, alternating, or direct current, which then in turn can cause corrosion to any metal materials that's in the path of that stray current.
Stray current corrosion occurs when a metal structure inadvertently gets in the path of current flowing in the environment between 2 other structures. This animation shows an underground tank, such as might be used to store gasoline, with an impressed current cathodic protection system to reduce the rate of corrosion. Cathodic protection will be described later, but it involves the passage of current from an anode to the part being protected through the ground, as in this case, or maybe through seawater. If there is a nearby metallic structure, such as a buried pipe, the path of least resistance for the current might be through the pipe. Where that current leaves the pipe to go to the tank, the pipe is polarized to a high potential and can corrode at an accelerated rate. Stray current corrosion can be mitigated by connecting the pipe to the tank electrically, and thus protecting both the pipe and the tank.
Now that we've examined the causes and effects of many types of corrosion, what do we do? Well, just as medical researchers have developed and continue to pursue ways to prevent or cure sickness and disease, so must we understand how to prevent or control corrosion. Our corrosion detectives have already developed many useful technologies and methods to successfully combat the corrosion menace, and their research and experience shows that, as in medicine, prevention is much more desirable and effective than treatment after that damage has occurred. These research and development efforts have been focused on 4 areas of corrosion prevention and control: prevent, detect, predict, and manage. Let's take a look briefly at each of these areas. Experience and rational analysis tell us that it is much more economical to prevent or try to retard corrosion up front than to expend our resources downstream to treat the effects of corrosion. We can accomplish that goal by selecting materials that are impervious or highly resistant to corrosion in the environment where these materials will be used. We can also thwart corrosion by designing systems so that one or more of the 4 elements of the corrosion cell cannot exist. So, engineers and scientists are continually looking for new materials and alloys that resist corrosion. Engineers also continue to explore manufacturing methods and treatments that will stop corrosion cell activity. Since corrosion is a natural phenomenon that is pervasive and invasive, we will never completely prevent corrosion or its effects. And while we can't prevent corrosion altogether, we need to detect it in its infancy, recognize what type of corrosion we're facing, and predict how rapidly it will propagate. We need to be able to detect and predict corrosion and its effects without damaging or destroying the structure that we're analyzing. Many innovative sensing and analysis technologies are available or under development, and other technologies and techniques are being investigated for future development. Corrosion can be managed in many ways. This process, however, has to be deliberate and planned. Paints, coatings, and other compounds have been used for years to try to offset environmental effects that contribute to corrosion. Such treatments are designed to protect surfaces from moisture, dirt, and other particulate matter that can complete a corrosion cell and initiate corrosion. Another management technique could be the use of shelters and protective packaging. Likewise, other management tools are being developed to allow the more effective use of corrosion technologies. Let's take CAS out of the standby mode and take a look at how coating degradation affects its corrosion protection performance.
Begin corrosion degradation program. One form of paint delamination is filiform corrosion, where corrosion forms a worm-like pattern under the coating that lifts off the paint. This phenomenon occurs on painted steels and aluminum alloys, although the mechanisms for each metal differ.
Another form of treatment widely used to inhibit corrosion, particularly in inaccessible places, is the application of corrosion prevention compounds, or CPCs. While CPCs are less permanent than paints, they are composed of organic compounds that contain inhibitors. These inhibitors are particularly important in preventing crevice corrosion. Cass, can we see an example of one of these CPCs?
Corrosion prevention compounds, CPCs, are chemical compounds that can be sprayed or brushed on to provide a thin protective coating. The life of such coatings varies, as does their performance. The video shows the effectiveness of different CPCs in protecting steel in a very severe coastal environment. The superimposed clock and visual effects provide some indication of the effectiveness of the CPCs in mitigating the corrosive attack. Eventually, this protection breaks down and the steel under the CPC starts to corrode. It is evident from the video that these materials have bought us time in the field without substantial corrosion. Paint systems are protective coatings, often containing corrosive inhibitors, which give much longer protection than corrosion prevention compounds. The time span of protection depends on the metal being protected, the severity of the environment, and the characteristics of the protective coating applied. However, defects in the coating can cause exposure of the underlying metal to the atmosphere and premature corrosion. These photos show examples of different coating systems on steel and aluminum exposed in a severe coastal environment. These examples include coatings with both chromated and non-chromated inhibitor systems. It is evident that a variety of coating degradation mechanisms exist.
Recent investigations by the corrosion detectives revealed that sheltering systems and equipment from certain environmental effects can significantly reduce corrosion. Let's take a look at this demonstration of the effects of sheltering. Cass?
Sheltering is an often overlooked method of corrosion mitigation. Sheltering is beneficial to materials because atmospheric corrosion is a strong function of the time of wetness and exposure to environmental corrodants. Sheltering may be achieved by merely placing a simple structure around equipment to be protected. The sample material on the left is composed of the same carbon steel as on the material on the right, which has been placed inside a tent at the same location. Sheltering, which reduces exposure to undesirable environmental conditions, such as chlorides and rainfall, can reduce corrosion rates by a factor of more than 10. The video shows that sheltering significantly increases the time for corrosion to initiate.
In designing for freshwater or seawater immersion, one of the most commonly used methods is cathodic protection. This method of corrosion control intentionally introduces electrical currents into the soil or water. This application of electrical current to a buried or submerged structure makes the surface of the structure act as a cathode in an electrochemical cell. Cathodic protection can prevent many types of corrosion, including uniform pitting and crevice corrosion in aqueous or soil environments. Let's look more closely at cathodic protection, which is used to suppress corrosion in ships, piers, water towers, pipes, and other similar structures and utilities.
Here, we demonstrate a corrosion suppression technique called Impressed Current Cathodic Protection, or ICCP. ICCP is used to protect underground piping, ships, piers, bulkheads, and water towers from corrosion. In this demonstration, we connect two steel nails to the terminals of a battery. The battery provides extra electrons to the nail connected to the negative terminal, thereby protecting it from corrosion. The cathodic current provided to the nail on the right, the cathode, results in the formation of hydrogen bubbles, but this nail is protected from corrosion and remains shiny. On the left side, the battery is extracting electrons from the nail, causing metal ions to go into solution, resulting in accelerated corrosion. You can see rust forming around the head of the nail and the resulting water discoloration.
I want to thank you for all your help today, Cass. We have investigated how we can prevent and control corrosion by effective material selection, design, manufacturing, use of coatings and other treatments, and application of electric currents. But if we are not successful in preventing or controlling corrosion, we must be able to find it and characterize it. So detecting and analyzing corrosion and its effects is extremely important for maintenance and repair, system readiness, and ultimately, material safety. We can see corrosion everywhere we turn if we just look for it. Corrosion wreaks havoc upon our valuable materials, equipment, and facilities unless we take positive actions to check it. We can no longer accept corrosion as a natural occurrence that should be ignored. Now that we have unraveled the mystery of corrosion and provided you with clues and insights into what it looks like, what it does, and what we can do about it, we can be more effective in our fight against it. Until next time, on behalf of Cass and myself, we bid you farewell, and remember, rust never sleeps.